These two formulas are so infamous. The first one is the Fourier transform, and the second one is the inverse Fourier transform. In mathematics, it is very important to know the derivation of any formula, so we don't use it blindly, but with a concept in mind. This video will dive into the derivation of Fourier transform and the inverse Fourier transform. I will explain them with many visuals. Let's go. Let us start with a square wave train. The width of each square is b, while the period of the signal is t. The Fourier series of this signal consists of upward and downward bars. These are obtained from the Fourier series formula. If we connect the ends of each bar, we will see an envelope that resembles a sinc function. How does the period of the signal affect the shape of the envelope? It turns out that the longer the period is, the smaller the peaks are. It will be very convenient if the height is not affected by the period. For this, we move the period t from the right side of the equation to the left side. Thus, the envelope has become t times c sub k. This will be very important in deriving the Fourier transform. In contrast to the Fourier series, the Fourier transform is commonly used for non-periodic signals. The square pulse is actually the previous square wave train with infinite period. If you increase the value of t indefinitely, you will end up with t equals infinity and just a single pulse. Return to the plot of Fourier series coefficients and see what happens if we increase the period. In that case, there will be more bars within each loop. It is easy to imagine that when the period approaches infinity, all bars will be so close to each other that we only need to be concerned about the envelope. This is the analytical expression of the Fourier series coefficients. When we set t to approach infinity, the integration limits will become minus and plus infinity. The envelope is t times the coefficient c sub k. We move t to the left-hand side and arrive at the formula for the envelope. The new name for the envelope is x of j omega, and don't forget to replace omega naught with omega. This is the Fourier transform of the time domain signal x of t. The right-hand side is similar to the calculation for Fourier series coefficients, except the discrete frequencies no longer exist, replaced by continuous frequencies. It is time for us to dive into the next problem. How do we obtain the inverse Fourier transform? This is the main challenge. If we are in the frequency domain already, how do we get to the time domain? We start from the Fourier series composition formula. This expression converts Fourier series coefficients to the time domain signal. Start by replacing 1 divided by t. The fundamental frequency, omega naught, is equal to 2 pi divided by the period t. It is pretty obvious that 1 over t is equal to omega naught divided by 2 pi. By substitution, we replace 1 over t after the summation with omega naught over 2 pi. Move 2 pi before the summation and omega naught to the end of the expression. Consider its graphical representation. The area of the rectangle is the term inside the summation. Let us scrutinize this rectangle further. The height of the rectangle is x of j k omega naught times the complex exponential. Horizontally, the rectangle starts at k omega naught and ends at k plus 1 times omega naught. The width is omega naught, and we shall change this to delta omega. Plugging it back to the original summation, we have something different. If we reduce the width of the rectangle to be so small that it approaches 0, then we can replace k times omega naught with omega and introduce a limit notation. The combination of limit and sum translates to an integral, with delta omega changing to d omega, a differential element. This is the inverse Fourier transform. Thank you for watching this video. Don't forget to hit that subscribe button so you will always stay tuned to our frequency. Leave your thoughts in the comment section below. See you next time.